Okay, so if we're using the brake A, that puts that first planetary gear set in reverse. Okay, because a clockwise input is going to result in a counterclockwise output. Okay, and if I have the sun driving the ring, that reverse, is that an underdrive, an overdrive, or a direct? So if you look at it, if the sun drives the ring, that's a little gear driving a big gear, right? So that's an underdrive. So we can add that in here, brake A, underdrive. Okay. If I go in forward and I lock clutch A, that's this one right here, that means the power flow is as shown. But if I lock any two components, in this case the ring and the carrier, what does that do to the drive? It's going to put it in direct. Okay. Then moving on, take a look at the other two gear sets. With these other two gear sets, I can either hold the ring or I can lock them together. So that means I either have an underdrive or a direct option for gear set B and gear set C. Okay. So in tracing the power flow that we have shown right now, we're in forward. Okay. We have the sun driving the carrier. So that right there means the smallest gear is driving the biggest gear and the ring is held stationary. That's a gear reduction, isn't it? Okay. And this gear reduction is going to go and drive the next one, but the next one we have two components locked together. We have the ring and we have the carrier locked together right here. So that's direct. Okay. So let's take a look at this and let's see if we can figure out what the combination would have to be. And we'll make ourselves a little clutch element, or I guess element chart here for this one. So we're going to have clutch and brakes A. We'll do it this way here. Clutch A, B, and C, and then we're going to have brake A, B, and C. Okay. So if I wanted to be in the lowest gear possible, which of these would I have to be? This will be first, forward. What would I have to use? Okay. Well, if I want to be in forward, that tells me that I have to use clutch A. Because gear set A, that's my forward and reverse selector gear set, right? So that means gear set A is going to be used. For gear set B, if I want to be in first forward, that means I want to use the reduction. Does that mean I have to use brake or clutch B? I have to use brake B, and that means I have the sun driving the carrier. So I'm going to use brake B. Okay, I want to be in first forward, so I want to get a gear reduction on the second planetary gear set. What do I need to do with that one? Brake C. Yeah. Okay. So I'll give you guys a quick second here, and let's try fourth forward. What would the combination look like for fourth forward? Okay, so we still need clutch A because that's our forward. And by the way, I'll tell you, there is only four. There's only four. Clutch B and clutch C, and that puts both of those in direct. That's the fastest this thing will go. So basically, we have a one-to-one forward drive through this transmission when we're in fourth forward. Okay. For second and third, it's just going to be a combination of whether I use brake or clutch B and C. Okay, because we have different sized sun and ring gears on those ones. That's why. So it's just a ratio combination of those. Okay. If I wanted to be in reverse, let's say reverse first, what would that look like? So it'd be brake A, brake B and brake C. So if I wanted to be in first reverse, all of the brakes and none of the clutches, right?
So the clutches hold the ring gear.
The clutches hold two members together. The brakes hold one member stationary.
Oh, okay.
That's how I'm defining those.
Just couldn't quite figure out what was what.
Yeah. So yeah, if I have a clutch on gear set A holding that carrier stationary, clutch, that brake holding it stationary, it can't move. If I have a clutch joining two of those components together, then they rotate as one. So usually when we're talking power shift transmissions, if it's a brake, it's holding something stationary. If it's a clutch, it's holding two things together, regardless of what that means. Okay. So this one here, we're starting to get a little bit of a look at what the power flow through planetary transmission looks like. I would say be familiar with this idea here. Okay. If you do come across any power flow questions as you're going through some of the tests coming up, make sure that power flow through a planetary transmission is something you're good with. Another one that we will have to be familiar with is power flow through parallel shaft type transmission as well. So this one here gets a little more complicated, but I like to use this diagram because it helps us kind of sort out what's going on inside of a transmission where there's several different things that have to happen to get one gear ratio out. This transmission, it has a speed section and a range section. Okay, so that means we can select some gears in, the low range. We can select some more gears in the mid range, some more gears in the high range. So really what's happening is I have a transmission that gives me a number of speed options, and then I can just multiply that by the number of ranges available. So in this case, how many speed options do I have? 6, okay? And range options? 3. So just basic math says this is at least an 18-speed transmission, okay? Now, it does have a creeper option. Don't worry about that. So an 18-speed transmission. What does a power flow look like through this transmission in first gear? Let's start there. Okay. So in first gear, power is coming in and it goes through. It goes through these gears over here. Okay. It's going to come across. We have this input shaft over here. This input shaft is going to be turning if the engine is turning. All right. If I want to connect that shaft to the counter shaft, I have to engage a clutch. All right. So the clutch, let's say that I want to be in first. Is that an even or an odd speed? Well, obviously it's an odd speed, right? So the counter shaft, this gray counter shaft is driven, and you see I have a clutch where I can join that gear that joins with the counter shaft. Okay. So that speed input shaft is going to join to this counter shaft down here, the speed counter shaft. And now the speed counter shaft, it drives this gear, and this gear, right? So I'm going to have power flow coming through here, and then I'm going to select the gear that gives me first. So I'm going to engage that clutch, okay? And then we're going to come up over here. So that means right now I have this odd clutch. I have the 1-2 speed clutch. If I want to drive the range transmission, I have to engage the master clutch, okay? Now, because I want to be in first, that means I'm going to select the biggest gear reduction possible. We're going to come down through here. This low clutch is now going to drive the output shaft, the range counter shaft, which is the output shaft of this transmission, which is going to drive the pinion. That's how this transmission ends up in first. Okay, but what this tells us then is that we have 1, 2, 3, 4 clutches selected just to get this thing into one gear. Okay. If I had a problem with a transmission like this, okay, and every single gear was giving me grief, and I check my transmission my transmission charge pump, and I see that all my pressures they seem to be okay. Like the pressure's there, but I can't seem to get this thing to move. There is one clutch that's common to every single gear. Your main clutch, your master clutch. Okay. If I have a customer complaint that this thing, it'll work in, second, third, fourth, eighth, or sorry, not second, third, fourth, second, fourth, sixth, eighth, 12th, and so forth. That right there says to me that anytime I'm trying to use one of the odd gears, it doesn't work. Probably a bad odd clutch, right? If I try to use, 1, 2, 3, 4, 5, 6, and it works, and then I'm missing everything from like 8 to 12, or no, sorry, 8 to 16. If I can get all the way through 6, and then everything seems to work right up until I get to 7th, no go. Okay, past 12th, and all of a sudden it starts working again. I mean, what would be the one responsible? That's going to be the mid-range, right? Now, when we're looking at power flows and transmission diagrams like this, from a diagnostic perspective, you're probably not going to look at a power flow diagram, but you will be looking at an element chart. Okay, and from a diagnostic perspective, you can use this, and this will help you figure out what clutches and what brakes are used for which gears, and then figure out which gears are having issues and see which clutch is common to all of those, or which brake is common to all of those gears that are having problems. Okay. So, for instance, this one here, can you guys just take a quick moment of your time there and see if you could tell me what the combination, and this one is always a combination of 4, what the combination would be for that 7th gear. Okay. So odd, 1, 2, master, and mid. And that'll put us in 7th. Okay. So yeah, if you come across a diagram where it shows you an inline transmission like this as opposed to a compound planetary, you can still trace your power flow through there relatively easy. Okay. If you have an element chart like this, you can take a look at this and see which clutch or which brake is common to what grouping of gears, and then maybe use that to figure out why you have a couple of missing gears in a transmission. Okay. We're going to talk a little bit about CVTs and torque converters, but I want to talk about the shifting over here. I thought I had a different diagram, so just give me a second. So this right here, calibrating a transmission, we're talking about clutches, we're talking about brakes, but the thing that we should also be talking about is how do you calibrate that? How do you calibrate clutches and brakes, and what exactly does calibrating actually mean? Right? So if you're calibrating a clutch or a brake, what we're really talking about is calibrating a wet clutch pack that's usually hydraulically applied and spring released. That's usually how it is. Now, when I'm trying to calibrate a transmission, what I'm really doing is I'm really teaching the controller how quickly that piston fills and that clutch starts to grab, right? Okay. So there's a chart that I like to draw, and we'll start with we'll draw it as a graph, okay? So if you guys want to follow along, here we have this graph. Okay. Now, if we take a look at how we apply a clutch. Okay, historically, this was done mechanically. That's not what we're here to talk about right now. We'll reference that in a second, but nowadays what we do is we use a solenoid. We use a solenoid to open a valve. That valve is going to send oil to a clutch pack. Okay, And that valve, depending on how far open or closed we have that valve, is going to dictate how quickly that clutch starts to apply, right? So the fill time, that's what I'm talking about there. And then the second part of the equation is how smooth do I want that clutch application to be? So we have the fill time, and then what's the other part of the calibration? Your modulation, your shift modulation. Okay, so those are the two parts, and we're going to try and represent that on a graph here. Okay, so we're going to talk about it in terms of current. Some people might talk about it in terms of voltage, but at the end of the day, what we're doing is we're using pulse width modulation to control the strength of the magnetic field on the valve, right? So if I want to engage a clutch, what I'm going to do is I'm going to turn on the current to the solenoid, right? And when I have that current turned on, it's going to take a certain amount of time for that piston to fill with oil and start to engage the clutch. And then as soon as that clutch starts to hit, what we'll do is we'll probably pull back on that current a little bit, okay? And then we're going to ramp up the current slowly until we get to the point where we have full pressure and the valve is fully open, applied to that particular solenoid, okay? So where this would be 100%, this might be 50%, and this might be 0%. So that means this first part here is fill, the second part is modulation, and a third part is hold. That's fully applied. Right? So understanding what's happening here, the shift modulation, because this is electronic, that shift modulation, that might be something that is more or less a soft value. It's something that we can change if we want to, depending on the operating conditions of the machine. If you have a machine, and let's use a dozer as an example. So if you're shifting gears on that dozer and it's not really pushing any heavy material or just kind of moving it from one spot to another, and you shift your gears on that power shift transmission, that modulation there, it might give you a nice, softer, gradual shift. But if you've got a really heavy load on the blade and you're pushing a lot of material and you do happen to want to shift into a different gear while that happens, that shift modulation is probably going to take place much more abruptly because we don't want to slip under heavy load, right? So that modulation, it's something that is, we could consider it to be variable depending on load, okay? Now if I take a look here, is this going to be heavy load or light load? This will be heavy load. And then this over here, that'll be light load. So we've talked about how this works. What we haven't really talked about is how we came up with these values. And the way that we come up with these values for what that solenoid should be doing, where we hit that 50% current or drop down and ramp it all the way back up to 100%, how did we figure out what those values should be? Well, we calibrate the transmission. That's what we do. Okay? And when I calibrate that transmission, I'm basically teaching the transmission control module how long it takes for clutch fill to happen. All right, so let's talk about why we would want to calibrate a transmission. Well, if you have a transmission and it's been used for a lot of hours, what happens to the discs in those clutch packs? They get thinner, and if they get thinner, that means the piston has to travel further before it actually grabs, right? Now, in the example that I gave you guys here, that fill time, it's just that, it's just a time, okay? And we knew that we had to have a certain amount of current going to that solenoid to open it up enough to get the fill time to what we wanted it to be. Okay, but if you have worn out clutches, your fill time actually looks like this. It's going to take longer, right? So the problem now is Your fill time takes longer. The transmission doesn't know that. And that means that it is going to think that the fill time ended sooner, so it's going to drop the pressure, and then it's going to ramp it back up again. Okay, is that going to give you a shift that feels like it's slipping, or is it going to feel like it's a lot harsher? Well, I got two options here now. Okay, so it actually takes longer for the clutch to fill. Okay, and then when I do actually start to ramp the pressure back up, as far as the clutch knows, I'm ramping it up further up the line here. So the amount of modulation time I have is less. Do you think that's going to make it slip or make it harder? If I spend less time modulating, it's going to feel like a harsher shift, isn't it? Right? So that's why when you calibrate a transmission and you retrain it, what are we actually doing? We're relearning the fill times. And when I relearn the fill times, I'm going to take and I'm going to adjust it for the worn out clutch so that I actually open up the valve further so that we're back to our original fill time. So I open up the valve further, I fill that clutch a little bit quicker to account for the extended period of time it takes to get to that initial point of contact. Okay. So we're going to call this one number 1, and we're going to call this one here number 2. And we're going to say for number 1, that's before calibration. There. And 2 is after calibration. Okay. So when I'm trying to calibrate a transmission here, there's a few things that I need to do. Let's talk a little bit about what that process looks like. So first order of business to calibrate is we have to have the thing at operating temperature. Why would that matter?
Oil expanded.
It's going to flow easier through the system if it's warm, right? So our fill times could be affected by cold oil. Most times if you try to initiate a clutch calibration sequence on a transmission, it's not even going to let you do it until you've got that up to temp. Okay. Now, when we're doing our calibration, what the transmission is going to do, or the transmission controller is going to do, is it's going to apply each clutch and see how long it takes for the clutch to apply. Right? So you're going to have it running at a certain RPM. You're probably going to have your foot on the brakes, and then you're going to hear as that calibration process is happening, the engine RPM is just going to dip a little bit every once in a while. Okay. And all it's doing is just measuring how long it takes to get the clutch to grab enough to pull the engine RPM down. Okay, so that's how it calibrates. And then it stores those values, and after it's got those values stored, hopefully it's a decent shift again. So you have to do this throughout the life of the transmission if you want to extend the life of the clutch and brake components inside of there. Okay. Do some transmissions have some adaptive learning where they can do this on their own? The answer is yes. Okay. Do you sometimes want to go in there anyways and give it a manual relearn just to make sure that it's exactly where it should be? Absolutely. Okay. Let's take a look at this chart here. I got some directional clutches and some speed clutches. You know, it is what it is. In terms of the fill and the hold values that we're shown here, these values, if these are going to be fill values for how long it takes to actually grab, and then hold values, I guess that's at the end, how long it took to get to where we get to hold. Whatever it happens to be, the fill values, I want to look at that. And I want you guys to tell me, based on the numbers you see, which of these clutches is the best and which is the most worn out. If this right here is, I don't know, maybe milliamps or something like that. Again, I'm not quite sure what this chart is telling us. It's just giving us the values in terms of numbers. But I would guess the higher the number, the more we got to have that valve open to get the correct fill time, right? So taking a look at the directional clutches, which ones of these are in the best condition? I'd say 1 and 3. Okay, number 4 looks to be in the worst condition. For the speed clutches, which is our best one? B and C, and the one that's wore out the most? A. Okay, so any questions on this?
Say if an operator comes in with like a hard shifting leak, would this be something you check right off the bat, or would it just be?
Okay, are you talking about checking these values here?
Yes.
Okay, if these values are something you have access to in your service software, you could certainly check those calibrated values. But realistically, if they got a harsh shift, I'd probably just try and run a calibration anyways, because these numbers here, if they were from a calibration that happened, I don't know, 2 years ago, how relevant is it? Do you know what I mean? So probably try to run a calibration on it. And after a calibration, if you do have access to this data, you can go back in there and have a look. And if you got one that is wildly out of line with all the others, that's telling you probably have a clutch that's quite a bit more worn out than the others. Is that kind of what you're getting at, though? Yeah.
Yeah, I was just wondering if this would be like an accurate diagnostic step that you would do.
I don't think that it would be the first thing I'd look at. I would do a calibration first. And then if you really thought that maybe you had a worn out clutch, looking at these numbers might give you a little bit more support, in that diagnosis. Okay. So there's another thing too that we can do to diagnose leaking or failing clutch packs, because you have to understand clutch wear is going to affect this. But if you end up with a severe hydraulic leak in that circuit that supplies that clutch, it's going to affect these times as well, isn't it? Okay, so we can't maybe just run a calibration and then send it out the door. Sometimes we do want to check our pressures, and when we check our pressures, I'm pretty sure you've seen that sometimes people will hook a series of gauges up to a transmission and look at all the pressures on all the clutches, right? Which is sometimes a legitimate way to diagnose. But the problem is, even in hydraulics, we said if there's enough pump flow to keep up with the leak, is the pressure going to be affected? No. Okay. So then that raises a bit of a question. How could we use pressure in the transmission to diagnose a leaking clutch? To figure that out, we're going to draw just a quick and dirty diagram over here, just to kind of show us what the circuit inside of a transmission would kind of look like. Okay, so we're going to start off with a pump. Okay, this pump here is going to represent our transmission pump. Okay, it's going to draw oil from the transmission housing. Okay, from there, it's going to go to a relief valve. Okay, this relief valve here is probably not called a relief valve. It's probably called something like a pressure regulator. Okay, and the reason it's called a pressure regulator is because we tap off in between the pump and that valve. We tap off to the shift valve, right? Okay, and then usually whatever oil we didn't need for the shift valve, we're going to use for something else. Okay, if this transmission had a torque converter, for instance, what we might do is we might put another relief valve in here. Okay, and this relief valve there we go. We'll have that one regulating torque converter pressure. Okay, so off to our torque converter. Okay, and then whatever's left, what do we do with that? We could just dump it into the transmission case, but we're probably not going to do that. What we're going to do here is we're going to run this oil along and then off to several different places in the transmission. Lube, right? So yeah, shift pressure regulator, torque converter pressure regulator, and then whatever's left over. And again, this is just a rough example of how this works, but end of the line is lube. Okay. Now, when I go off to my shift valve, if I had, let's go ahead and let's make this my shift valve. If I had a couple, I'm just going to draw two here. Okay. So the shift valve, it's going to open and close oil to those two pistons. Those pistons being the ones that engage a clutch. So if one of those pistons has some severe bypass here, but it's not enough to end up using up all the flow of the pump, and we take a look at a gauge. Okay, so I'll put a gauge over here. We'll call that one gauge number 1. Put a gauge over here, gauge number 2. Put a gauge over here, gauge number 3. So 1 is shift pressure, 2 is torque converter, 3 is lube pressure. If the leak on that one bad piston there isn't bad enough to take up all the flow, is the pressure at number 1 really going to be affected that much? No. Okay. There's constant flow there, but there is enough pump flow to keep up with the leak. Number 2, it might be affected, but you know what's definitely going to be affected? Number 3. So measuring transmission lube pressure, a lot of Powershift transmissions are plumbed so that whatever leftover oil there is the lube oil. If you measure lube pressure, that's a really quick way to find out where the leak is. Okay, so something that I remember doing quite often is instead of getting gauges on every single clutch port that you have available on the shift valve, just plumb into the lube. Okay, and then go ahead and shift through all of the gears in the transmission and monitor your lube. Your lube pressure as the transmission shifts, it's going to be here, and then it's going to dip and then pop back up. It's going to dip and then pop back up for each gear. And then when you get to the bad gear, it's going to dip and it's going to stay down because that one is leaking. Okay, that piston is leaking, and that means there's less flow left for lube. And if there's less flow left for lube, your lube pressure goes down. So lube pressure with an internal leak. Okay. What's interesting is we've said that a lot of times in a Powershift transmission, one of those clutch packs, it's not used just for a single gear. Often it's used with a combination of other clutch packs, and it's used several times for different gear combinations. So what I'm going to do is I'm going to run this lube test that I talked about, and I'm going to note every gear that we had that pressure drop happen in. And then I'm going to take, and I'm going to go back to that clutch or that element application chart, and I'm going to see of all of those ones that I identified when that lube dropped, which clutch or which brake was common to all of those that had an issue. Now I've got a really, really pointed diagnosis, don't I? Okay, so I can do the calibration. I can look at those fill times, and they will be affected. This here is a really good test to tell exactly what the problem is and how bad it is. And is it a mechanical problem or is it a hydraulic problem? This is a good test for it. Okay.
Would you be able to print out the copy of the transmission? Right down the bottom period.
This stuff here?
Yeah.
Yeah, I can do that. I'll do that after we're done in class.
Yeah.
Really. I'll make a chart like I did with the other ones for you guys. Yeah. Okay. So any questions on what we've talked about here so far?
So that breakdown at the top there, are those all stationary clutches or is there a rotating clutch? Just my diagram at all?
Are you talking about this one here?
Yeah.
Okay, so the clutches, they're going to be rotating because they're part of the rotating assembly. The brakes, those are going to be stationary, right? Yeah. When we're talking about transmissions, when you're assembling a clutch pack like that, what you're going to want to do is you've got splines. Excuse me. You got splines that mesh with the internal part and splines that mesh with the external part, right? And you're going to have your separators; those are the steels, and you're going to have your clutches; those are the friction discs. So anytime that you're assembling a clutch pack like this, it's important that all those splines are lined up. You got to make sure that that clutch material has been lubricated, probably soaked in the same type of oil that you're going to be using to assemble the transmission, or to put into that transmission after assembly, I should say. And the other thing you should do is you should test those clutch packs prior to, going ahead with the rest of the assembly. What do I mean by that? Well, it would sure suck to get a transmission fully assembled just to find out that you had a cut sealing ring that you damaged when you're busy putting this thing together. Okay? That really, really sucks. You know what? It sucks when it happens, but I would way rather find that out when it's components on a bench than having the whole machine assembled full of oil and trying to use it and something doesn't work right away. So how do I test this while I'm busy putting together the transmission on the bench? Yep, blowing air into it is exactly what I would always do. Okay, you get out your blowgun with that rubber tip, find the port that goes to that particular clutch pack, blow some air into it and see if it engages, and also see if it leaks. Okay, and also see if it releases properly too, because if you don't put the springs in proper and it doesn't want to release, now you got a dragging clutch. Okay. A clutch that hangs on an old assembly could be the hub, or it could be the drum, where you have those discs basically wearing little grooves into it, so they get locked into those grooves, and even with the pressure gone, the clutch wants to drag. That can be another source of a harsh shift. Okay. Now let's assume that we're talking about real world, not this theory stuff here. Real world, are you ever going to actually rebuild a transmission? Very, very seldom. Okay, but what you're probably going to do is take out an old one and put a new one in, right? And when you do that, are you going to be changing the transmission controller every time? Are you going to reuse the controller that was in the machine originally? Yeah. So if you're changing out an old houred out transmission and you reuse the same transmission controller, there's something you'd better do before you send that out. Otherwise, it is going to have some extremely harsh shifting. You better recalibrate it. Okay? And if you don't recalibrate it, it's going to think that the fill times are this long, and it's going to slam those gears in so hard, whether it stalls it or whether it just jerks that thing around like crazy and causes some other damage. It's not going to shift very nice. So when you put a new transmission in, or if you've rebuilt the transmission yourself or you're putting in a reman, those fill times are going to be totally different than what those old calibrated values were from that old transmission. So always recal. Okay, so we got a little bit of time left here. We're going to spend some time talking about torque converters. And we're going to spend some time talking about CVTs. Where do we see continuously variable transmissions in the heavy equipment industry? It's not very common, but one application would be some wheel loaders use this. Okay, a CVT is very, very common over on the ag side of the industry. And regardless of whether it's in a wheel loader or whether it's in a farm tractor, a CVT is usually, it can be quite complicated, but if you break it down to what actually makes it a CVT, it's a combination of a hydrostat drive system and a planetary gear set. Okay. So looking at this, I just wanted to show you guys the basic notion of how this works. You have your inputs, that's your engine. It's shown in green. Power flow from the engine is going to drive one component of a planetary. And this is completely normal for all the CVTs out there. We drive one part of a planetary, whether it's the sun, whether it's the ring, whether it's the carrier. We just drive one part of it. Okay. So one part is driven by the engine, the other part is the output. And the third part, instead of just holding it like we normally do with the typical planetary, we can control the speed of the third component. And we control it with a hydrostat. Okay. So whether it's a ring gear or a sun gear or a carrier, it doesn't matter. In this case, my power flow comes in and then it goes through the carrier. Okay. So in and through the carrier. And then given that this is a planetary, theoretically it could go to the sun or the ring from here, right? Now, if I trace it and take a look at what the ring is doing, the ring is this gear that's driving a hydrostat pump. Now, the hydrostat pump, when it's in neutral, can it freewheel? Is there any real resistance to it turning? No, there's not. It'll just sit there and spin if it wants to, right? So that means that the ring gear can absolutely spin if it wants to. And let's check the rest of the power output here. Okay, so we came in And then let's go and see where this sun gear connects to. The sun gear connects to something they're calling a collector shaft, okay? It's kind of like a counter shaft. And that collector shaft is connected to hydrostat motors. In this case, they're showing 2 of them. There might only be 1. It doesn't matter, okay? But there is the motor part of the hydrostat connected to that shaft. So if the pump is freewheeling and the motor is stroked over, is the motor basically hydrolocked at this point? Let me rephrase. If the pump is in neutral, is there any oil going to the motor? There's no oil going to the motor, so the motor is not going to turn. Okay. Oh, okay, settle down here. The motor is not going to turn. All right. And if the motor can't turn, that means this collector shaft, it's not turning. Right? And if the collector shaft isn't turning, then I have this other gear here. I actually have 2 gears. One is a high speed, one's a low speed. Okay, so it basically gives you 2 ranges, 2 mechanical ranges on the output of this. It's going to head on over here to the axle. All right. But if none of that is turning, this machine is stationary. Okay. The engine is turning, and that means the ring gear is turning, but nothing's happening. Okay, this is neutral. Now, if I want this machine to start to drive, then what I'm going to do is I'm going to start to swash over. I'm going to start swashing over the pump. And as I swash over the pump, what's going to happen is it's being driven by this ring gear, right? But it's going to start sending oil down to the motor. And if it sends oil to the motor, it's going to start hydraulically driving the motor, isn't it? And if I start hydraulically driving the motor, that means I am hydraulically driving that output. And that means I am actually going to start driving. So the more I swash that hydrostat over, the faster that hydrostatic motor drives that collector shaft. Okay. Now, once I get to the point where I've got that pump swashed all the way over and the motor is spinning as fast as it can, what if I want to go faster? Well, now what I'm going to do is I'm going to start de-stroking the motor, okay? Once the pump is fully stroked, then I start to de-stroke the motor, and it's going to spin faster and faster, isn't it? Okay. And if I get to the point where I have the pump fully stroked and then I fully de-stroke the motor, that hydrolocks the hydrostat. So think about that for a second. If we hydrolock a hydrostat, that means that nothing's turning. Okay, so now I have the motor fully de-stroked and the pump fully upstroked. That means the pump here, it can't pump oil. It's stuck. It's stationary. And that means the ring gear isn't turning either. And that means the carrier is driving the sun gear 100% mechanically now. So this machine here starts off from basically 0% speed and 100% hydraulic drive. And then as we start to get closer and closer to maximum speed, we get closer and closer to full mechanical drive. When we're at maximum speed, we're full mechanical drive. Okay. And what's also interesting about this machine is if you want to go in reverse, all you do is you swing the hydrostat pump the opposite direction, and that pumps oil backwards to the motors. And then reverse on this one is 100% hydraulic. So reverse is 100% hydraulic. Anything from 0 all the way up through until you get to max speed is a blend of hydraulic and mechanical. Okay. This one here is the easiest hydrostat to understand. Okay. I shouldn't say hydrostat, I should say CVT. There are other CVTs out there that use a combination of what we're talking about, the planetary gear set, the pump and the motor, and then they have also like a 3 or 4 speed range transmission, a Powershift range transmission built into it, and they're basically just shifting back and forth through the sweep of the pump and the motor. Now, why do they do that? Probably because Fendt had already patented the best way to do it. Okay? Because this is a Fendt Vario CVT transmission that we're looking at here. This is the simplest, best one. These ones are tough. You don't hear about guys having problems very often with the transmissions on these. Okay, you take a look at the CVT that you have in a John Deere tractor, a Case tractor, or a cat wheel loader, and those are enough to make you pull your hair out. Okay, these ones pretty straightforward and tough. What we're looking at here, where we take and we use a hydrostat to control the rotational speed of one part of a planetary. This is also very much the same idea of how diff steering works, right? So diff steering, what I'll do is I'll take an axle and a couple of planetaries, and instead of those planetaries being normal final drives, those planetaries have a sun gear as the input. And again, we're going to draw just a really simple, quick diagram of this. So here I have my crown and pinion gear set. Okay, there is no differential to speak of here. Okay. What I have is a couple of solid axles. Those solid axles, they drive a set of sun gears. Okay, the sun gears are going to have these planetary carriers here. Okay, those planetary carriers are going to be connected to, say, drive sprockets. Okay, because we're probably talking about a dozer here. Let's be honest. Okay, so those drive sprockets, this is my final drive. Okay, but the final drive, instead of it having fixed ring gears, which we're quite used to, the ring gears aren't fixed. Okay, the ring gears, they actually have teeth, and I'm describing a really simple one here. So if you're really familiar with the cat one, this isn't exactly how they do it. I'm just drawing a simple diagram of the basics. So what if we took a shaft, okay, and had some gears on it? Okay, so that shaft is going to have a couple gears. It's going to have a commonly driven shaft, and we are going to have a motor over here that has a pump. I'll try and draw a pump here. So that pump, there we go. This is our steering system. Now, how the heck does this work? Well, the pump can turn forwards or backwards, and that's going to turn the gear over here forwards, and because I stuck an idler on the other side, it's going to turn that idler backwards. Or I could hold the whole thing stationary, and then it is just basically a normal final drive. And if I spin that hydrostat the opposite direction, then those ring gears, they end up turning the opposite direction. Okay. How does this work? Well, just like we said with our CVT, if I can change the rotational speed of one component of a planetary, I can change the effective output ratio of that planetary. So if I speed up the ring gear on one side and slow down the ring gear on the other side of this differential steering system that I have here, that effectively makes one of my final drives a lower ratio and one of them a higher ratio. So this right here, this is how we do differential steering. Okay, that's the reality is it's usually a bit more complicated than this, but the idea of what's happening is pretty much this. We're speeding up one side and slowing down another. There is no differential, even though it's called differential steering, interestingly enough. Okay, the differential, or what we think of as a differential, is just a crown and pinion gear set driving the transmission. Okay. We might have a fluid coupler at the front of a transmission. We might have a fluid coupler at the back of a transmission. The fluid coupler at the front, that would be what we're looking at here. This is a torque converter. Okay, so a torque converter is going to have 3, 4, 5 main components, depending on how you want to look at it. The 3 main ones that we're seeing here, the impeller, the turbine, and the stator. Okay, so one of these components is driven by the engine. That would be the impeller. Okay, and if we think about what's happening inside of here, this whole assembly is contained inside the housing, and it's full of oil. It's pressurized. It's not a huge amount of pressure, but it is pressurized oil. Okay, now that impeller, when it's turning, centrifugal force is trying to sling oil out of it, right? And as it slings that oil out of it, that oil is going to hit the blades of the turbine. And as it hits the blades of the turbine, it's going to impart some force onto that. Well, I guess depending on how fast the impeller is turning, that may or may not be enough force to actually get an engine to spin. Okay? Or not an engine, the transmission output shaft, the turbine shaft to spin. That's what I meant to say. If I do have the transmission in gear, and I've got the engine revved up high enough, there's going to be enough force to cause the turbine shaft to start spinning. The turbine's going to start spinning. There is going to be quite a speed difference between the impeller and the turbine. There's a lot of that centrifugal force throwing oil in the circular fashion that we see here. This is called vortex flow. Okay, vortex flow is when you have, let's write this down. Okay, so vortex flow is when you have the most speed difference between impeller and stator. Not stator, turbine. Okay, and then rotary flow is when you have the least speed difference. Okay. So right now, with a good amount of vortex flow happening, that means that the oil that's being slung around inside the torque converter here, it's going to try to leave the inside part of that turbine. Okay, and if there's a huge amount of speed difference between the impeller and the turbine, that means there would be a lot of turbulence in this area over here. Okay, and turbulence is where I'm mixing around oil but not really doing any good work with it. Okay, so instead of having a bunch of turbulence there, which would end up robbing horsepower and creating heat, what I'll do instead is I'll have this thing called a stator. And a stator is basically just a cup-shaped vein that is going to take that oil leaving the turbine, and it's going to kick it around and help it to hit the impeller blades more or less in the same direction that the impeller is already turning. Okay? It's just a way to kind of smooth out that oil flow inside my torque converter. And when I smooth out that oil flow, at this point, I'm doing two things. I'm reducing the turbulence, but I'm also increasing the torque slightly. Okay? Because as I kick that oil back around and it starts hitting the impeller blades on the inside, that actually amplifies the torque a little bit. So you can get a little bit of extra torque out of a torque converter. As this oil starts to, I shouldn't say as the oil, as the components of the torque converter start to turn as one cohesive unit, the impeller is going to be turning at nearly the same speed as the turbine, and that means the stator, if it was still being held stationary, it would create a lot of turbulence over here, wouldn't it? In these two areas. So rather than have that happen, we have a one-way clutch that allows it to unlock, and it allows it to freewheel and turn with the rest of the oil that's turning as this kind of a donut inside of the torque converter. That's what we call rotary flow. It's all turning the same. Rotary flow, you'll notice I said there is the least speed difference. I didn't say there was no speed difference, because there's always going to be a little bit of slippage inside of a torque converter. For efficiency, nowadays, it's really normal to put a clutch in between the turbine and the torque converter housing, okay, or the turbine shaft more correctly. Okay, that torque converter clutch, we can lock that up, and that locks effectively the transmission input shaft to this entire torque converter assembly, and that gives us a true one-to-one. Okay. So that torque converter clutch, it locks up for one-to-one drive. So torque converter testing. Torque converter testing, the test that we do to see if a torque converter is working or not is a stall test, right? So a stall test, what we're going to do is we're going to warm the transmission up, make sure that the oil and torque converter is warm, and then we're going to do a couple things. Okay. We're going to select high gear. All right. We're going to have our foot on the brake. That wouldn't count on the park brake being strong enough, and most transmissions won't let you shift into gear if the park brake is engaged anyways. Okay. So I'm going to put my foot on the service brake. Okay. Wide open throttle. And monitor engine RPM. Okay. So those are the conditions. And if we have a problem, then our engine RPM is going to be the thing that tells us that we have a problem, right? If your RPM is too low, what could cause the RPM to be too low during a stall test? Okay. Now, I know that you've probably talked about this before and things like engine RPM being too low because of underpowered engine and all that kind of stuff. I'm asking you, what could be wrong inside the torque converter that would cause the engine RPM to be too low during a stall test?
Stock stator.
Okay, so the stator freewheeling or the stator not unlocking?
Not unlocking.
Okay. So during a stall test, the stator is supposed to be stationary, and it's supposed to redirect the oil flow, and that's supposed to help the thing and reduce turbulence inside. If it's not locking, it's going to introduce turbulence that shouldn't be there, and that's going to take horsepower. So which one do you think would be, locked or unlocked? If the stator is always freewheeling. Okay, if your RPM is too low, that is probably a stator freewheeling, and that can cause a lack of power on the low end. If your RPM is too high during a stall test, oh, hold on a second, it just jumped over there on me. Slipping transmission could certainly be that. Low viscosity or lack of oil supply to the torque converter. Could be an overpowered engine, I suppose, if somebody's got that thing tuned. Okay. Now, for the stator and that one-way clutch, let's assume that we do have a one-way clutch, and let's talk about a one-way clutch that's stuck, like you brought up there. So a stuck one-way clutch, is it going to be doing what it's supposed to be doing during takeoff anyways? The answer is yes. So we're not going to notice a problem on takeoff, but it doesn't get out of the way when it's supposed to up at the top end of the operating range of this torque converter. So that means a stuck one-way clutch where the stator doesn't unlock is going to cause a lack of top end speed and probably overheating during extended use at higher speeds because there's a lot more turbulence inside of there. Okay. If you have a stator that's freewheeling all the time, it won't lock up. Now you're going to have a lack of power on the low end because you're not getting that torque boost from it, and it's actually robbing horsepower because it's introducing turbulence where you don't want.
Got overheated too.
It'll definitely overheat because of the turbulence on the low end. Yep, for sure. Here's another one, and this does happen. Personally, I've only noticed it on the automotive side. But sometimes you have a machine or a vehicle where when you take off from a stop, it seems like it shudders and then it starts to drive normally. Have you ever experienced that or heard of that? So it's shuttering on takeoff. Okay, what do you think the cause of that is? If it had something to do with the torque converter, seeing as how that's what we're talking about now, what would it be?
Stator not locking up.
So the stator one-way clutch, it does not lock up predictably. It seems like it spins a little bit before it actually locks. Okay, so if you have a shutter on takeoff, there's a really good chance that that shutter is this one-way clutch in the stator slipping until it finally locks during takeoff. Okay.